All right, so today we are going to be looking at indices. Now, this is obviously a new topic, but it kind of follows on from some things we've done before. Now, I have here kind of two of these examples, which were taken from a previous video I did about the effect of squaring something or cubing something. And we looked at this, and these are an example of indices, but our powers, these little things up here. So when we look at, for example, 2 our base number squared or 3 our base number cubed, we looked at this almost as a type of shorthand. And that's how we can interpret indices. They're essentially a shorthand for writing a bunch of different multiples of the same number. So instead of here writing 3 times 3 times 3, we can just write this as the base number with some power, which is the amount of these values that multiply. So this can extend towards higher powers. So I briefly touched on this in that other video as well, but say I had, 4 lots of 4, lots of 4, lots of 4. We have 4 fours here, and it's the same number. So we can write that as 4 to the power of 4, in the same way that we've done these two up here. Now let's look at let's introduce kind of indices and how they interact. And this is pretty much just going to give you hopefully an intuitive look into how, let's say, it'll pretty much give you a look into the first law of indices. I'll call it that. So let's look at one example here. So let's see what would happen if I multiplied 2 by 2 squared. So this is sort of, well, let's look at what we're essentially doing here. 2 squared, this just makes up 2 lots of 2, doesn't it? Because we have our base number and we have 2 2's that multiply by each other. So this is kind of like writing, well, 2 times 2 times 2. We could have also taken another approach. We could have said, all right, well, 2 squared is 4. So that's like going 2 times 4, 2 times 4. And what do we get in each of these scenarios? Well, we get 8 here as well as 8 here. So hopefully none of this is really new to you in terms of multiplying these numbers. But let's actually write each of these, our 8, we can actually express each of these as our base number, because that is kind of prevalent here. We can express 8 as a base of 2 to some power. And we essentially write this as, we can say 8 equals 2 cubed. Now, why 2 cubed? Well, in the same way that we looked at before, we have 3 2's here. And that is how we got our power. But is there a type of general law we can come up with when we multiply the same base numbers? Well, there actually is. And this is that any number, any base number, let's call it A, when, let's say A to some power M, when that's multiplied by A to some power N, we get that as the same base to the power of a sum of these two powers. Now let's actually verify that. I'll actually move this here a little bit. try to center this more a bit. Well, let's look at what happened in each of these cases. Well, 2, any number can be represented as itself to the power of 1. So when we multiplied 2 to the power of 1 by 2 to the power of 2, well, when we actually split these up, we kind of just wrote this as, well, this is just 2 to the power of 1 times 2 to the power of 1 times 2 to the power of 1. And adding 1 3 times, 1 plus 1 plus 1, gives us a 3 here. It's the same as if we had 1 plus 2 here. If we didn't decompose this in this way, well, adding my powers, I just get the same base just to the power of 3. So this is effectively just a shorthand way of writing. It's pretty much a shorthand way of writing multiplication of same base numbers. And it works for any powers. So, and we can actually verify this as well. So let's look at another example. All right, what if we did, say, let's go 5 squared times 5 cubed. All right, well, what is 5 squared? That's just 5 times 5. And 5 cubed is 5 times 5 times 5. Well, we have 1, 2, 3, 4, 5 fives here, right? And what's important to know, this only works because this base number is the same. If this was like 5 squared times 3 cubed, well, we can't just say that's, 15 to the power of that sum. No, we need the same base here. Now, this is like writing, well, 5 squared plus 3. And we would get 5 to the power of 5, which is essentially what we have up here. By decomposing this, we have 5 different 5s all multiplying by one another. And the general kind of rule for this is this thing that I've drawn here. This is the effect of multiplying indices. So multiplying numbers of equal base and different powers. They can be the same powers as well, but anytime we multiply same base numbers, we can add their powers together. That is pretty much the first rule of indices. And you can even verify this thing here. If you typed into a calculator 5 squared times 5 cubed, well, you'd get 3,125, which is the same as if you just wrote 5 to the power of 5 into a calculator. So we've essentially verified this law here. That is how indices work when we multiply them. And what's important to note is that any number, even if we just had 5, so say here, in each of these cases, we just have 1 5. So this is like saying 5 to the power of 1, 5 to the power of 1, 5 to the power of, I'll do a different color just so it matches. We have 5 to the power of 1, 5 to the power of 1, and 5 to the power of 1. Adding 1 plus 1 plus 1 plus 1 plus 1 gives us 5 in our power. So in essence, this is the law that relates everything we've talked about. And in the next couple of videos, we'll look at a few more patterns that arise. I'll see you guys there.